Hello there. So I'm going to make a series about quaternions. I think they're some of the most difficult things to understand. Um, well, I'll put it this way. There are rocket engineers and stuff who realize they have to sit down and study quaternions, and not everyone can wrap their minds around it. Even it's difficult for rocket scientists and people studying theoretical physics and stuff like that. So it's a very high level, difficult thing, partly because these are four-dimensional objects. Okay, now I'm not going to explain the super basic fundamentals of quaternions, because there's lots of sources out there that will do that. Maybe I'll make that video in the future. However, this is going to be many videos, because it takes time. If you're impatient, then quaternions are not for you. This is something that's very hard to understand. Okay. Now getting into it, we have this cube here, and I have chosen these colors. So the x-axis, you can see there's red. So it's RGB, right? Corresponding to X, Y, and Z axes. So we have X is red, Y is green, Z is blue, as is apparent here, as you can see. Now, I have chosen kind of opposite colors for the opposite sides. So what does that mean? Well, what is the opposite of red, right? Well, red, the way I'm choosing to do this is the opposite of red is cyan, which means you have complete blue and green, but no red whatsoever. And so that's cyan, which is over here. If you have 100% red and green, but no blue, you get yellow. And if you have 100% red and blue with no green, you get magenta. So that's CMY, which is another color scheme used for... It's famous for being used with printers and stuff, but there's maybe other reasons. And you notice that the CMY is brighter than RGB, because it has kind of twice the color saturation, if you will. Okay, so that's the basic cube startup, and it's a good exercise if you're new to all this stuff to try to get this into your game. It actually was kind of a headache for me. I mean, it took a couple hours learning all this stuff about Blender. This was the way I did it. Maybe you can find a easier way. Okay, now I have this script attached to this cube, so let's take a look at that. And I've got some bunch of other stuff that I have been trying doing, and I've commented them out, as you can see. But maybe you get some ideas by looking at that stuff. But now I want to talk about the quaternions. Now, again, I'm not going to go over the super basics. Well, not properly. I'll kind of mention them because it's a necessary reminder. So they're basically four-dimensional objects. However, when we use quaternions for rotations, I can't remember if this is true in all contexts, but at least the way it's being done here, we have to do what's called normalization. Okay, so what is normalization? Well, can I bring up paint? I don't know if I should, honestly, but okay, let's give it a go. You have a sphere, let's say. So a sphere, I mean the normal, like a soccer ball kind of sphere. I do a lot of math stuff, so I would say the sphere that is naturally embedded in 3 dimensions. In math, people like myself refer to this as a 2-dimensional sphere because the surface is 2-dimensional. But it's your ordinary run-of-the-mill sphere here. You might be like, what? Why is this person being so specific? Well, mathematicians talk about n-dimensional spheres. You can have spheres of different dimension. And a 1-dimensional sphere is actually a circle. This ordinary one is we call it a 2-sphere, okay? Anyway, sorry, it takes me some time to write stuff out. Maybe I'll get a Wacom or something, but the ordinary sphere you refer to as a 2-sphere. Now, Also, when math people talk about spheres, they never, ever, ever, ever are referring to filling in the inside, okay? That would be, that's called a ball. A 2-ball would be the sphere, but it's filled in. So, okay, so here's a 2-sphere. So what I'm doing is I'm going to explain normalization in this 3-dimensional case with a 2-sphere. Okay, we say the 2-sphere that's the sphere that's naturally embedded in 3-dimensional space. I'm being a little pedantic if I say the 2-sphere that's naturally embedded in 3-dimensional space, but I hope you get what I'm saying. And so, what would normalization look like here? Well, we have the origin, which is the point 0, 0, 0. Okay, I can't explain all of, like, I guess at a minimum these are Cartesian coordinates. You need to know Cartesian coordinates. But you probably want to know a little bit about vectors because, well, if you're watching this about quaternions, you've probably already seen about vectors. But, I mean, vectors are they're kind of deep when you get into mathematics. There's like easier versions of vectors, if you will, that are, say, if you're a game programmer, and you've never taken a college course on linear algebra, then you probably are not aware of maybe the more technical definitions of vectors. The technical definitions of vectors allow you to do more abstract things. So I don't want to get too far afield here, but so maybe I'll make other videos on vectors at some point, but pretend this is a straight line and you have some vector coming out. Let's say that it is intersecting the sphere like here, or something that's coming out of the sphere, and it goes to this point. And we always, so if you're a linear algebra person, you always imagine vectors coming out from the point 0, 0, 0. Now, more generally, we can talk about, like, you have various objects, and you have, I don't know, some object and some force over here, and then you have it's applied to an object, and you have another force over here, and these are vectors and all that. So in general, say in your classical or your physics 101 class, you can have vectors point in different places. But in a linear algebra context, they all come out from 0, 0, from the origin. Whatever, if it's a 2-dimensional space, it's 0, 0. For 3 dimensions, 0, 0, 0, etc. So, okay, so we take this vector and we just squash it onto the surface of the sphere. That's normalization. Okay, so let's take another example that's simpler to calculate. If you had this vector going straight up. So it could be whatever the point is, doesn't really matter. It could be, let's say, 0, 5, 0, for example. But when you squash it down to the sphere, it is going to be 0, 1, 0. Okay, and so what's the formula, the general formula to calculate this? Well, it's based on the formula of a sphere, x squared. I really need to start using a Wacom. So the waifu has a Wacom tablet, so I need to borrow it one day. See how it goes. This is the general equation. Am I getting this right? I think that's right. Yeah, for a sphere. So if it were a circle, I just want to show you the general pattern. And I know many of you, or maybe even all of you watching this, maybe have been exposed to this before or know it quite well. Here's the equation of a circle. This is the equation of a sphere. So what have we done? We've added the z squared. But notice it didn't go to z cubed or something. So this kind of, yeah, distance keeps working like this. So if we were going to make it 4-dimensional, we would add in like a plus something else squared. So like, for example, plus w, because we ran out of letters, so we go back to w squared, okay? But it's still squared. And then if, actually, I said distance. So this is related to the formula for distance. Basically, so the distance formula in 3 dimensions will be this with d squared instead. So usually you'll see it written instead d equals the square root. When you square root, sometimes you do plus or minus, but we don't usually talk about negative distances. Yeah, so I always think of it as equals d squared, and so I said that, yeah, this is a sphere. Well, this is a unit sphere, I should have said. A unit. So it's actually the proper, I know I'm kind of jumping around, sorry about that, but the proper formula for a sphere is with the r squared. And same here. For a circle, this is a 2 sphere, this is a 1 sphere actually. It gets a little confusing. The 1 sphere is the sphere that is naturally embedded in two dimensions. It's always one higher. Oh no, I should actually use the brush to delete this. Oh my goodness. Oh my goodness. I just thought this was getting in the way. Anyway. All right, so we have, okay, so general formula for a sphere, that's a sphere that's naturally embedded in 3 dimensions, and here's for 2 dimensions. So we can actually use this, we can kind of use the general distance formulas. Oh no, it's redoing that. No. Oh, whatever, we're going back. We can use the general distance formulas, so I'll go like this. D equals square root. Okay. But in this case, because we're talking about the unit sphere, so I should have been saying the whole time the unit sphere. Sorry about that. Now, all I'm doing here is describing normalization. But we set it equal to 1 because we're talking about the unit sphere. Well, you could say 1 squared, but that's the same as 1. So this is the equation. So if we have to normalize this, to normalize, there's maybe a little bit more thinking we need to do, because I haven't made this into an equation that you can just plug this in here. So I have to do some more vector-y kind of stuff. We want this unit vector times some scalar. I don't want to go too deep into it. You can look up more about normalization if you want to. But this is the intuitive picture I wanted to communicate, which is that things are getting smashed onto a sphere. But where things get a little bit tricky is we're not talking about, with quaternions, we're not talking about 3 dimensions. We're talking about 4 dimensions and the 3 sphere. This 3 sphere is a 3-dimensional space, which is the natural sphere that is embedded in a 4-dimensional space. Now, so let's see here, 3 sphere. So note that when we have a sphere, you might say, well, yeah, I can kind of see that it's a 2-dimensional surface. Like it's like you have the globe. You could have a map of the globe. I should have drawn this a little bigger. I just want to say we often, like if you imagine there's a sort of line down the, from let's say the North Pole to the South Pole, and then you have like the equator going around like this. We often call this angle theta. You can kind of remember, see theta looks, am I getting this one right? Yeah, this one I think is theta. It looks like a globe cut in half already. And the other angle, it often comes down from here, but it doesn't have to. I think it can come up from there as well. That one is phi, I think, usually. So you can see that it splits. It looks like it splits the globe down from top to bottom, whereas theta, and theta sometimes is written like this, more directly. Maybe that's a capital theta, and then like, or whatever. You get the idea. So anyway, you use 2 angles to define a unique position somewhere on the globe. So a unique position on the globe we can use that to give us an axis of rotation. So 2 parameters to determine a axis of rotation. And then we need a third parameter to decide, for example, if this is our vector, how much we're moving around along that axis of rotation. Okay. There's one more thing I want to say. This is a little extra, maybe, but I think it's super, super interesting. This whole story of an axis of rotation, because I think this is extremely confusing for people if you don't inform them of this. They might get extremely confused someday. I have been confused. The story of an axis of rotation only works in 3 dimensions. What actually we should be talking about is not axes of rotation, but something else called bivectors. But, that's a whole other can of worms. But a bivector just it's composed of 2 vectors. So you have 2 vectors and they kind of form they can form, let me draw it like this. The 2 vectors can form a parallelogram, basically. 2 vectors always form a parallelogram, like this. They also always form a triangle, too, but that's just half the parallelogram anyway. And we kind of talk about the area of this space as being a bivector. But yeah, it's getting too complicated. But the reason I want to point out this whole axis of rotation business is it's a bit nonsense in a way, because it only works in 3 dimensions. 2 dimensions doesn't have enough space technically to create such an axis. And so when you get into 4 dimensions or 5 dimensions, etc., there's no axis of rotation. What you're doing is you're rotating between 2 parameters, basically. What's the right word? 2 variables, right? You can have some big n-dimensional matrix. Let's keep it simple and say it's a 3x3. And for example, let's put a 1 here, and then if I put cosine of theta, negative sine theta, and then zeros in these spots. This is a matrix that can rotate about the x-axis. But if it's a 4-dimensional matrix, then it goes all the way down here. These are zeros. When it's 4-dimensional, talking about an axis like that doesn't make any sense. No longer makes any sense. So this axis of rotation business only works in 3 dimensions, and we're all dumber because in a sense, we're all dumber because we're stuck thinking about 3 dimensions. What's really technically a good way of talking about it, which I shouldn't get into, but this is how I'm doing things. You should really think of this as an eigenspace of the transformation that happens to be a vector in 3 dimensions. It's a one-dimensional subspace in the 3-dimensional case, but in a 4-dimensional case, it would be a 2-dimensional subspace, which would form a plane and so on. So the technical way is to talk about eigenspaces, or at least I think that's the smarter way to talk about it. Okay, I know that's overwhelming. It's a bunch of craziness. We don't want to get too lost in all this stuff. But normalization is just smashing onto a sphere, except in the case of quaternions, you need to add 1 dimension to this entire story. Now, if you want to think about what's the best way to? I don't want to bring up. Can I scroll down? Oh, whatever. We want to think about 1 more dimension. So, well, some people say, oh, you can't think of 4 dimensions because we live in 3 dimensions. We really live in 4 dimensions. We live in 3 dimensions of space, 1 of time. So you can imagine like a sphere, and you have another parameter that collapses the sphere down to a point. Okay. You can imagine little baby spheres in here. And then, am I doing this right? I think maybe it's actually the opposite of this picture. So let's imagine this picture first, even though it's wrong. It can collapse it down into a point, and then you can build it up again into a sphere. Try imagining that, but I think it's actually the opposite. Is it? I don't know. So, to me, these are inverses, and it's, in a sense, they're just opposite. They're duals. They're the opposite of the same story. So I switch back and forth in my head of imagining these things. But you can also imagine a sphere that is stuck as a point, and then you increase it, and it becomes sort of full size, and then you can decrease it again. This is probably, I don't know. So we can imagine this is when the W vector is maximal in the positive, and here it's -1. Yeah, so in this case, the sphere that you're imagining is everything that's not W. So if we're talking about X, Y, Z, W, then you have that. And this one, maybe you forget about that one. I find this one interesting as well. But nonetheless, maybe it's inappropriate for what we're talking about. Anyway, so you can imagine this, you can use time and imagine more parameters here. What's a little hard is trying to imagine more stuff like, okay, you're here, what directions can you move? It does get tricky, but it's an excellent exercise, I think, to try to imagine what a sphere would look like in 4 dimensions, the 3 sphere that is naturally embedded in 4 dimensions. And the picture, remember this theta phi picture, we have a similar thing where on the sphere, we only need 3 parameters. But this is all, that changes everything, because look here, we have, for the 2 sphere, our ordinary soccer ball sphere, we can either describe it with 3 parameters, the x, y, z parameters, or we can describe it with 2 angles, the theta, phi. And both of these are legitimate. In a way, you don't need 3 parameters. So if you're thinking of systems of equations, you've added one equation, which is this distance formula setting equal to 1. And so now you don't need, if it's a system of equations, you no longer need all 3 variables to describe it. You only need 2 variables. Okay, so we have both of these options here. So now when we talk about the 4-dimensional case, we have options with x, y, z, and w, or you can imagine with 3 angles. I don't know what you call the other one. Phi, theta, phi. What's the good next one? I don't know. Gamma, whatever you want. And I find it. I've tried to think sometimes about. I try to imagine the 4-dimensional picture in my head and try to imagine what would it look like to switch between these 2 pictures. The 4-dimensional one with the w squared and the 3-dimensional one with the angles. And can I imagine switching? And it's not easy. It's also interesting to study topology a bit, and of this sphere, you can kind of unwrap the sphere into some kind of rectangular shape. The distances here are sort of like smushed or something, but don't worry about what the inside here looks like. If you and what topologists do is they put arrows on the sides here so that, let's say this one goes that way, and I think, yeah, this one, these are pairs, these 2, and then whichever arrow you put, I guess you could go either way. These are going to be pairs as well. There's another object. Well, you could also look at a torus, and the difference is the torus, which is basically a donut shape, can also be unwrapped into a square, except that these arrows work differently. I think you can also have it, depending on how you choose the dimensions, you can have it so that the space is actually flat here, I think. Don't quote me on it, but I think maybe you can have like a nice little flat space in the middle. I won't attempt to draw that though. But I think on a torus, yeah, the arrows are coming out differently. So these opposite ones are pairs together. Okay, and then you could have other shapes, like there's a Klein bottle shape, which the arrows are pairs across from each other, but they're going in opposite directions. They get flipped as you go around. That's a Klein bottle. But okay, so trying to unwrap this in your mind and thinking about what it's like to move around in the space is a warm-up before you try to think about 3 dimensions, the 3-dimensional case of the 3-sphere. Now the advantage is that because we live in 3 dimensions of space, we can imagine 3 dimensions okay. But the difference is that on the sphere, there's curvature, so things wrap back around. So it's like... Hold on, something was making a weird sound. It's like you're at some point in 3-dimensional space, and no matter where you go, if you just keep going straight, you will come back. You'll go all the way around the world and come back to where you were. But things get weird if you say go here, turn by 90 degrees, go here, and it's just raining outside. It's tripping me out. Depending on the angle, or sorry, depending on the distance, if you go the correct distances, you can actually turn 90 degrees but come back to where you started. These are all 90-degree turns. So it doesn't look right, but think about it on the sphere. If you started here, you did you went 90 degrees along the equator, so you're here, and then you went 90 degrees up here. Did I do that right? No, I did that wrong. You start here, you go up to the North Pole, so you just go straight. You turn 90 degrees, you go down to the equator, you turn 90 degrees again to go now west, and then you go straight, and you come back to the place you started. So it's like there's these weird triangles where there's three 90-degree turns, but wait. Yeah. Normally in a triangle, the angles add up to 180, but because there's curvature, this adds up to 270. But if you go a smaller, this is called parallel transport, but if you go smaller distance, the smaller the distance that you go, the closer it'll be to flat, which is 180 degrees. Okay? So there's curvature. So even though you're thinking of a 3-dimensional space for the 3-sphere, the surface of the 3-sphere, it's not going to, what's the word? It's not flat. It has curvature. So it's a bit of a tricky space. But you can try to imagine it as this kind of retro game world where if you go really far in one direction, you come back to where you started. That I find easy to imagine. Of course, you need to do it in all 3 directions. What's harder to imagine is this like coming where space is fundamentally curved. That's the hard part. So imagine you're moving around on the surface of this 3-sphere, and try to imagine that you're carrying this vector that points towards the center. And how would that vector move as you move around the surface of the 3-sphere? It's very confusing. But I invite you to try to think about that. Okay. So quaternions, so they're normalized. So I'm just going to minimize this. They are normalized. So the cframe.new, you give it an x, a y, a z. That's just a position. And you can give it the 4 characteristics, or sorry, 4 parameters for quaternion. It goes x, y, z, w. The w one is a special one. It corresponds to the scalar component of the quaternion. And x, y, and z. So you need to look up about how quaternionic rotation is done. But your x, y, and z correspond to the I, j, and k imaginary, or sorry, I should say it the other way. I, j, k correspond to choosing some axis. Okay, and that's done in like this straightforward manner, and then your so it will find, yeah, so you give it an ijk, that will correspond to some x, y, z. Now remember, it's going to get normalized, but we're not doing the normalization yet because there's also a w, and this is going to correspond, generally speaking, it should correspond to how much you're moving. Okay, I'm going to comment these, I guess. But W is roughly how much you're moving. But before these things get done, the 4 parameters that you give it get normalized. Okay. So this is a little tricky maybe to understand right off the bat. So let's comment this and look at a slightly, let's slow things down and do more one at a time here. Let's just set this to 1. Now, if your W goes to 0, there's going to be, the object just disappears. It's like, don't let it get to 0. So here's x, y, z. So in the z component, I put this math.sine of t. T, I'm calculating, we have the original time gets set with the tick function. And I was actually adding +1 to t. No, I don't need to be doing that anymore. So anyway, so we have our t is basically time in seconds since we started the program. And that gets plugged into the sine function. What's great about cosine and sine is the outputs are always between -1 and +1. So anytime you want to test something and like vary something a bit, you can use these. If you want to vary the thing that you're testing by, like, let's say 25 units, you can do this, and it will vary from -25 to +25. That's how that'll work. So I'm just varying between -1 and 1, and then we have a 1 here. So let's see what happens with the rotation when I do this. Let's have a look-see. Okay, so you can see it is rotating like -90 degrees, between -90 degrees and +90 degrees. A full rotation of pi from one extreme to the other. But it, sorry for the scary face, huh? Is this like a Majora's Mask thing or what? I don't know. Somebody let me know where that's from. Or is it a Naruto thing? I'm not sure. Anyway, so you can see that, remember, the red one is, when there's no rotation, is pointing directly to the right. That's the x-axis. So you can see it going -90, +90. Okay, so let's try to make sense of what's going on here. So this is varying from -1 to 1. So yeah, it's weird. So I'm actually get a little confused because I feel like so I'm getting confused in real time. I feel like it's normalizing this separately, but let's see. So if I add, like, if I make this 20, what's going to happen is that here's what I think is going to happen. This is a really big number. Okay, so when it normalizes, what happens is it shrinks everything. And so it will shrink this down by quite a lot in order to make the full distance. The magnitude of the quaternion is supposed to be 1. That's normalization. We call that magnitude of the vector. The length of the vector, essentially. It needs to be 1. So you have to divide and it normally it divides everything by the magnitude. So I kind of showed it here a little bit. If your magnitude is 5, like it is here, you would divide everything by 5. So what can I give as an example? So let's just say, I hope I'm not wrong here. This is annoying to erase. Let's say if you had a 3, of course it'd be pointing in a different direction. And let's make this... No, I'm not doing this right. This is not... Definitely not the way I want it to pan out. Anyway, it divides all of them by the magnitude squared. So it calculates the magnitude based on this distance function and divides it by the magnitude squared in order to normalize the vector. So that's what I was missing before in my explanation. I told you there's a little more work you got to do to normalize. That's what you do. You take the vector and you divide by magnitude squared. So here we have a quite big magnitude. It's more, well, yeah, it'll be always more than 20. Well, it's actually, this is getting squared, but then square rooted. It'll always be more than 20, the magnitude. So it's dividing by a number that's at least 20. So what that means is this is going to be always really small. At most, it will be 1 over 20. It'll be between like negative 1 over 20 and positive 1 over 20. And this will be slightly less than 1. Okay, so let's see. And I think we're just going to see not much. Because this z part is small now, we're not going to see much rotation now. Yeah, we see a lot less rotation because of the normalization. Okay. But what kind of confuses me, I have to admit, is that when this is 1, that you get a full pi rotation. What happens if we do 1/2? Because if it were 0, 0, 0, 1, then that would be 1. All right. Right. So here, I feel like maybe it's sort of normalizing it. So I don't know. I had everything making sense in my head before I started making this video. But anyway, because this example up here makes sense. Let me try to talk about this example. So what I've done is I want a vector that is going to be distance 1. So I need more space here, but here's the idea. It's kind of take a 2-dimensional cross-section of what we're doing, because I'm only working with z and w right now. The x and y don't really matter. Okay, so we'll say this is z and this is w, for instance. And let's say, so w will set equal, if they were both 1 over square root of 2. 1 over square root of 2. You're going to see why I'm choosing these numbers in a second. Then when we use our distance formula, which is calculating the magnitude, same thing, we have the square root of x squared is 0, y plus y squared is 0, plus z squared is 1/2, plus w squared is also 1/2. So we get the square root of 1, which is just 1. So if w and z were both 1 over square root of 2, there's no normalization that needs to take place. It's fine as it is. So here I've placed 1 over square root of 2. And here, remember the output of sine, it varies from -1 to +1. It starts at 0. Okay, so the average is 0 over time. But so at an extreme, when it's at its maximal value, it will be 1, and this whole thing will be 1 over square root of 2. So let's see what happens. So now what we see, how much is that rotating? I did something weird in the beginning, didn't it? What was that about? Can I see that again? I feel like it jumped in the beginning. Oh, you know what probably just happened is that something with the delta time in the frame rate just, I don't know, it was janky for the first couple frames, but so we're actually seeing basically the same thing as before. We're seeing this rotation from between -90 degrees and +90 degrees, which makes sense to me. But I mean, I'm honestly getting confused. I don't know why. I'm either having a brain fart or I haven't fully understood it yet. But when we have 1 here, we get basically the same behavior as in this example. See, that I don't quite understand. But if you increase this to a big number, then the amount of rotation is slowing down. And if you change it to a small number, the amount of rotation increases. Which I think... and that's because this number, in turn, when you make this number big, what's happening is this is getting smushed to close to 1, but this one is getting smushed to something really low, and the opposite is true when you make W really low. So I think I get it, okay, but I think I'm just having some trouble explaining much more. So I will think about this a bit more, and I will try to come back with a much better explanation, but this is just part 1, and there's a lot more to talk about, and I'm going to be exploring these things and making it more clear. I have experience using quaternions for more complicated applications. They're actually, you can use them for a lot of deep stuff in physics. Not only electromagnetism, but spin of electrons. All the spin in quantum mechanics works. But you could use quaternions. Normally people don't. But you could. So anyway, so I think I'll wrap it up there, and stay tuned for some better explanations. I need to think a bit. But I shared quite a bit of stuff. I don't want to delete this video. Maybe someone else can leave a good comment explaining. See, I can't even think clearly enough right now to figure out if I'm confused or not. That's the thing. I'm not sure if I'm misunderstanding or not. But one thing's for sure is I'm at my limit right now of ability to explain what's going on. So it's almost 2:40 a.m. where I am, so that might be part of it. Anyway, I know this is kind of all over the place, but if you have it in your hearts, stay tuned. All right. Thank you. Have a good one. Bye.